Our lives are filled with tests, right? From the SATs that get us into college to the assessments we take for a new job. But have you ever stopped to wonder what actually makes a test good? It's definitely not as simple as just getting the answers right. Today, we're going to pull back the curtain on the science of validation and see how experts figure out if a test really, truly measures what it claims to measure.
We've all been there, staring at a test, feeling the pressure, and thinking to ourselves, is this thing really going to predict if I succeed? Will this score show if I'll be good at this job or do well in this program? It's a huge question, and honestly, it's one we should all be asking. And hey, it's not just a personal question. Big institutions are wrestling with this too. Right now, there's a major debate about the LSAT, the law school admission test, and it all boils down to this one single concept: validity. Does the test actually do what it says it does? That's what we're going to unpack right now. So, here's our game plan. We're going to start with why consistency has to come before accuracy. Then we'll get into the 3 main ways researchers gather evidence. After that, we'll look at some real-world challenges, how validation works on a massive scale, and why this is a process that, well, it never really ends. All right, first things first. Before we can even begin to ask if a test is accurate, we have to know if it's consistent. I mean, think about it. If you don't have consistency, you've got nothing. It's the absolute bedrock of any good measurement. And that consistency has a name. It's called reliability. Here's a simple way to think about it. Imagine a bathroom scale. If you step on it, step off, and step on again, and you get 3 totally different weights, that scale is not reliable. A reliable test is just like a good scale. It gives you basically the same result every time under the same conditions. Okay, so once we know a test is reliable, that it's consistent, then we can ask if it's valid. And here's the crucial part. Validity isn't really about the test itself. It's about the conclusions, the inferences we make based on the scores. So if we conclude that a high score means someone is going to be a fantastic leader, validity asks, is that conclusion actually true? Let's go back to that bathroom scale. Imagine it always tells you you're 5 pounds heavier than you really are. Every single time. Well, that scale is reliable. It consistently gives you the same wrong answer. But it's not valid, right? Because the inference you're making about your weight is incorrect. For a test to be valid, it has to be reliable and it has to be accurate. And this brings us to an unbreakable rule in the world of testing. Reliability sets the ceiling for validity. A test simply cannot, under any circumstances, be more valid than it is reliable. If the measurement itself is all over the place, any prediction you make from it is going to be wobbly too. Now, don't worry about the math here. You don't need to calculate anything. Just focus on what this formula means. It's the mathematical proof of what we just said. It shows that a test's unreliability literally puts a hard cap on how valid it can ever be. It drags down its potential. That's why you have to prove consistency first, before you can even start talking about accuracy. So, how do researchers actually prove a test works? How do they build the case for its validity? Well, they don't just rely on one thing. They gather 3 different kinds of evidence, which we can think of as the 3 pillars of validation. Pillar number 1 is content-related evidence, and this one is pretty intuitive. It basically asks, do the questions on the test actually match the subject it's supposed to be about? You wouldn't want calculus questions on a test about Shakespeare, right? Good content validity means the test is a fair and representative sample of the stuff you're actually supposed to know. Here's a fantastic real-world example of how this works for a job test. You don't just make up questions. You start by doing a deep dive into the job to figure out the essential skills needed. Then you bring in experts to help write questions, and here's the kicker. Every single question has to be explicitly linked back to a specific skill required for that job. It's a super systematic process. Our second pillar is called criterion-related evidence, and this is all about prediction. With this one, we care less about what's in the test and more about whether the scores can predict a real-world outcome, something we call a criterion. That criterion could be anything: your GPA in college, your sales numbers at work, or even your success as a pro athlete. And a perfect example of this is the 40-yard dash at the NFL Combine. I mean, running 40 yards in a straight line doesn't really look like playing football, does it? But decades of data show that a player's time, the predictor, is strongly related to their success in the league. The test is valid because the scores predict an outcome that NFL teams care about a whole lot. Okay, our third and final pillar is construct-related evidence. This is the deepest level.
It asks, what invisible trait, what underlying construct is this test really measuring? Things like intelligence, creativity, or leadership are constructs. You can't see them directly. This type of validation is about proving that your leadership test is actually measuring leadership and not just, say, someone's level of confidence. So, how do they do that? Researchers use a smart two-pronged attack. First is convergent validation, where they show that scores on their new test are related to scores on other older tests that measure the same thing. Then comes discriminant validation, where they show the test scores are unrelated to tests that measure different things. By showing what it is and what it isn't, they build a really strong case.
So gathering all this evidence sounds pretty logical, right? But here's the thing. The real world is messy, and there are some major challenges that can make validating a test a real gauntlet. One of the biggest problems is something called range restriction. Let's say you give a test to 100 job applicants, but you only hired the 20 people with the top scores. Well, later on, when you want to see if the test predicted job performance, you only have data on that small elite group. By cutting out everyone else, you've restricted the range of scores, and that can make your test look way less powerful than it actually is. Look at this table. It shows the damage perfectly. When you look at all the applicants, from low scores to high scores, you see a nice, strong relationship. But if you only look at the people you hired, the ones with mostly high scores, that strong relationship just flattens out. The correlation can plummet. It's the exact same test, but the data gives you a really misleading picture of its predictive power. And then there's this other sneaky problem called shrinkage. This happens when you create a prediction formula based on one group of people. It gets tailored to all the little quirks of that specific group, so when you try to use it on a new group, it just doesn't work as well. The solution? It's called cross-validation. You build your formula on one group, and then you test it on a completely separate, fresh group to see how well it holds up. It's a crucial reality check.
So with all these real-world problems like small sample sizes and range restriction, how can anyone be confident in a test's validity? Well, the answer is to zoom out and go big by combining the results from tons of different studies.
And this powerful technique is called validity generalization. You can think of it as a study of studies, or what scientists call a meta-analysis. Researchers gather up hundreds, sometimes thousands, of previous studies on a topic. By pooling all that data together, they can finally filter out all the statistical noise from the individual studies and get a much clearer picture of a test's true predictive power across the board.
And that brings us to what might be the single most important takeaway from all of this. We always want to ask, what's the validity number for this test? But that's the wrong question. As R.M. Guillaume put it, validity isn't a single number. It's an argument, an inference that you build from all the evidence you can find. It's an ongoing scientific investigation.
So we'll leave you with this thought. The next time you're facing a high-stakes test, try thinking like one of these researchers. Don't just ask if the test is fair. Go deeper. Ask for the proof. Ask about the content evidence, the prediction data, the construct it's supposedly measuring. Because understanding validity isn't just academic. It's the key to critically understanding the tests that shape so much of our world.